to introduce Professor Bill Goldman of the University of Maryland, College Park, USA, and he will be speaking on dynamics and classification of geometry on surfaces. Professor Goldman, please.
Thank you very much for to the organizers and the scientific committee for the invitation. It's a great honor to speak at this conference honoring Raghunathan's birthday. What I'd like to describe is how the project in differential geometry, the classification of locally homogeneous geometric structures on manifolds, leads to some very interesting dynamical systems, both in homogeneous dynamics and inhomogeneous dynamics. And I'd like to survey some of the examples, some of the success stories in the classification of geometries. And then this leads to an interesting class of cubic surfaces and their automorphisms, which I'll finish with. So when I say a geometric structure, I mean a very special kind of structure, namely a locally homogeneous structure. That is this collection of coordinate systems that are locally modeled on a geometry. And a geometry, I will mean in the sense of Felix Klein's Erlangen program, that it's the properties of a space invariant under a transitive action of a Lie group, namely a homogeneous space. The basic examples that I want to describe will be flat Riemannian metrics, which I'll think of as Euclidean structures, manifolds that are modeled on Euclidean space with coordinate changes, local isometries, hyperbolic geometry structures, metrics of constant negative curvature, and we can introduce singularities into the structures by allowing the coordinate charts to not be local diffeomorphisms, such as isolated singularities with specified cone angles. These are very important in the previous example of Euclidean structures, where translation surfaces or abelian differentials or quadratic differentials on Riemann surfaces have played a very important role, but I don't think I'll have much time to discuss that. Some of the structures that I will discuss include affine structures. These are the same as flat affine connections of zero torsion, but I want to think of them as being structures modeled on affine space with locally affine changes of coordinates. So these are like linear manifolds, if you like. And closely related are structures modeled on projective space, both real and complex. And since there's such a huge variety of flavors of geometries and homogeneous spaces, this is a very rich subject. So what I mean by classification is finding some moduli space such that the points parameterize the equivalence classes of structures. So the example that I like to give to non-mathematicians is that the two-sphere has no Euclidean structure. So there are many proofs of this fact. That means that there's no globally defined world atlas that preserves Euclidean geometry. So I want to fix a topological space, usually a manifold, say a real analytic or smooth manifold, and look at ways of modeling that manifold on, on a homogeneous space. So the example that I want to give, I'll come to this later, will be Euclidean space. We will model it on Euclidean space with a group of isometries, and we want to find an extra structure of a marking, like in Buch's talk, which will be a topological coordinate system, which will the extra structure will give rise to a more tractable space. So that'll be the deformation space of GX structures on sigma, where GX corresponds to the action. And these actions will correspond to actions of the mapping class group of changing the marking. So the first example I want to give is quite familiar. Euclidean geometry is the geometry of Euclidean space invariant under its full group of isometries. I want to normalize the volume and choose an orientation to make the statement simpler. And then the topology I want to take will be the n torus sigma. And different Euclidean structures correspond to different lattices, and the quotients are the Euclidean manifolds. So in the deformation space, in the deformation space, that will be the space of lattices, but with the marking will correspond to a basis. So a marked lattice is nothing more than a basis of the vector space Rn. The deformation space is the space of marked lattices is just up to the equivalence relation of isometry, will just be the homogeneous space of bases of Rn under the special orthogonal group. So that's the symmetric space of SLNR. The mapping class group, which is this changes the markings, will just be the action of SLNZ acting on this space. And SLNZ will be acting properly on the deformation space. And therefore we can form a quotient, which is the locally symmetric space. And that's going to be the moduli space of flat tori. So this is a nice model for what I mean by a classification of geometric structures where the underlying topology is the n torus and the geometry is Euclidean geometry. Another example, which is not quite a geometric structure in my sense, but it's closely related by uniformization, is the classification of Riemann surfaces. And going back to Riemann, there is a nice space that parametrizes the Riemann surfaces of fixed topology. It's known that this Riemann moduli space has a lot of rich structure. It's not quite a manifold. It has some singularities at the symmetric Riemann surfaces, and that's true also for the preceding example of flat tori. A more tractable object is the Titular Space, and that consists of a marked Riemann surface. And that's a metric space, a complex manifold, contractible space of dimension 6g, real dimension 6g minus 6. A marking will be a diffeomorphism of the fixed topology sigma to the Riemann surface M. And we want to include this structure so that the Riemann surface can vary, but the topology of sigma is fixed throughout the discussion. Then the equivalence classes will then correspond to the mapping class group orbits on the Titular space, and the Riemann moduli space is the quotient. So these are two examples where the classification is quite nice. The deformation space is contractible and easier to understand than the actual quotient. And this is one way of understanding the mapping class group and other groups, arithmetic groups that would arise as automorphisms of the topology. So let me briefly review what I mean by a geometric structure. The geometry is represented by the homogeneous space, X with a transitive action of G. The topology will be the manifold, usually a surface in this talk, and we'll have a universal cover and fundamental group, and the marking is a diffeomorphism of the fixed topology with the geometric manifold. The geometric structure will be defined by a coordinate atlas consisting of patches, defining local coordinates modeled on the geometric space, the model space, the homogeneous space, and then overlapping patches, the coordinate changes will extend to transformations in G. That can be unwound to give a map, which is a local equivalence from the universal covering space and a representation of the fundamental group by deck transformations acting now through G on X. The development global, the coordinate charts, and the holonomy homomorphism, the homomorphism from the fundamental group, globalizes the coordinate changes. We would like to build a space, like a moduli space or a deformation space, and so we take a marked geometric structure, and that'll call that the deformation space. The association to the representation of the fundamental group defines a mapping from the deformation space into the space of equivalence classes of representations of the fundamental group into G. In general, these spaces can be pretty pathological. Anything that could go wrong can go wrong in specific examples, but the best cases, for example, hyperbolic manifolds, these spaces stratify into smooth manifolds, and this mapping tries to be a local diffeomorphism. Changing the marking corresponds to an action of the mapping class group, and the orbits, if the orbits will then correspond to this, whatever the moduli space is. However, generally the action won't be proper, and this will lead to an interesting class of dynamical systems. So the example I gave of the Riemann moduli space and Titular space is familiar and fits into this framework using the uniformization theorem. Namely, the complex structures on a surface of higher genus identify with hyperbolic structures, and therefore the Fricka space, which is isomorphic to the Titular space of hyperbolic structures, is now a model of this classification of geometric structures. The going back to work, I think maybe Andre Weil should be credited for knowing that the space of hyperbolic structures embeds as an open subset in the space of equivalence classes or representations, and the dynamical system is, as I mentioned before, proper, and the quotient identifies with the Riemann moduli space. In particular, the Euclidean analog, which is simpler for the torus, the deformation space of unit area Euclidean structures identifies with the upper half plane. The modular group GL2Z acts properly by linear fractional transformations, and one has a very nice dynamic. Dynamically, that's not very interesting, but function theory is quite interesting. I want to describe some examples now of where the dynamics is more interesting. Maybe it's worth mentioning that in the case of surfaces of higher genus and projective structures, say manifolds modeled on the real projective plane and their group of collineations, then we also get a nice quotient. But this is actually rather exceptional. If we look at structures on a 2 torus, then the Oliver Bowes proved that the deformation space identifies with the Euclidean plane, but the action of the mapping class group is the usual linear action of GL2Z. Let me say a little bit about these examples, which I think deserve to be better known. All the Euclidean structures are equivalent under the relation of affine isomorphism, because they all correspond to different lattices, and lattices, a marked lattice is a basis, and the change of basis defines a linear conjugacy between the two actions of the lattice. So the origin will correspond in our description of a complete affine structure on the torus, which happens to be Euclidean. The others, though, are obtained by a conjugating by a diffeomorphism, and the diffeomorphism is about as simple as it can get without being affine, namely it's quadratic. And the pictures at the top of the screen show how this quadratic diffeomorphism bends the lattice and changes it to a new one. And these structures, I think, go back to Kuiper around 1950. Specifically, if you conjugate by this diffeomorphism, a simple and pleasant calculation shows that the quadratic terms introduced by phi cancel out, and what's left are the cross terms, which define an affine transformation. Now, the linear action of the mapping class group of the torus, which is GL2Z, is quite chaotic. It's no reasonable quotient. On the other hand, the Euclidean area is invariant. It follows from Moore's ergodicity theorem of 1966 in homogeneous dynamics that the action is ergodic with respect to this area. So every invariant function is almost everywhere constant, and almost every orbit is dense. However, there are plenty of discrete orbits, for example, the integer points inside Z2, and all the other rational points where the denominator is bounded. So the dynamics is quite complicated, and we wouldn't really want to take a quotient like the moduli space of flat tori or the Riemann moduli space. So let me say a little bit about general properties of this of these moduli spaces. That in the case of when the fundamental group is a surface and the surface is oriented, then there's a natural symplectic structure on the space of equivalence classes of representations. In particular, the symplectic structure in the case of a closed surface will restrict to the symplectic structure arising from the Weil-Petersen-Kähler structure on the Titular space. Now this is on the space of hyperbolic structures, and this will also be defined on hyperbolic structures where we allow certain singularities and enter other connected components of the space of representations. In the case of compact groups, for example, the unitary group, the symplectic structure, the natural symplectic structure, to my knowledge, was first discovered by Narasimhan in 1970, where he wrote down a formula in terms of flat connections and differential forms. And later this played a key role in Atiyah and Bott's structure description of the moduli space of flat unitary bundles in terms of stable holomorphic vector bundles over Riemann surfaces, which Narasimhan and Seshadri developed from a more algebro-geometric context. And so this generalizes the symplectic structure on the Jacobi variety when n equals 1. In the remainder of my talk, I'll mainly describe what happens when the surface has boundary. In that case, the space of equivalence classes of representations, sometimes called the character variety, inherits a Poisson structure, and the Casimirs, the invariant functions, will correspond to fixing the conjugacy class of the representation around the boundary. And the fibers, the symplectic leaves, will be the symplectic manifolds upon which the mapping class group of the surface will be acting. So I'd like to describe, here's a few, I'll mention a few general principles. First, the components of the space of representations are, when G is a compact Lie group, are indexed by the elements of the fundamental group of the derived subgroup. So if G is semi-simple, then this is the fundamental group is finite and the connected components are indexed by these, by elements of its fundamental group. This is also true for complex semi-simple groups as well. The mapping class group action will be ergodic on each component of the, when G is compact, of the representation variety. I had proved this in the case of SU2, and then later this was generally proved by Doug Prickrell and Eugene Zia. Particularly, ergodicity implies a statement about representations of the mapping class group, that only the only vectors that are fixed under the mapping class group are the constants, and that's a more general fact is that these actions are weak mixing. The only finite dimensional invariant subspaces inside L2 are the constants as well. When G is non-compact, a lot's known. It seems reasonable to expect that the actions are ergodic in all the components except for the component that Andre Weil identified as the Titular Space, the Fricka space. And recently, Marche and Wolf showed that in genus 2, there are 3 types of components: the maximal components, where you have a proper action, the ergodic actions, and the other components, the Euler class 0, which corresponds to representations in the PSL2R, the lift of the universal cover. They're actually two ergodic components. The main technique for proving ergodicity is to use the symplectic geometry and to show that the Dane twists are similar to Hamiltonian flows defined by looking at length functions and trace functions on the variety. So I think in the remaining part of the talk, I'd like to describe one particular example that leads to some very interesting and very concrete dynamical systems, and in particular, some affine cubic surfaces defined over the reals. So the topology that I want to take will be when sigma is the one-hole torus. So in this case, the fundamental group is a 2-generator free group. I'll be looking at the space of representations of that fundamental group in SL2C. There's a very nice answer which goes back at least to 1889 in a paper of Vogt, which says that the character variety, the space of equivalence classes of representations of the fundamental group, is given by an affine 3 space. It's given by, its coordinates are very simple to write down: the traces of the 2 generators and the trace of the product. You can think of this as a very algebraic version of the side, 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 and angle, angle, angle test for congruence in non-Euclidean trigonometry, whereby the free group of rank 2, you can be thought of as a index 2 subgroup in a free Coxeter group of rank 3, and the fundamental domains, if you like, for structures correspond to triangles. In that case, the angles of the triangle, or dually the lengths of the sides, will correspond to the traces of these generators. But we're interested in the case of the punctured torus, and in that case, the boundary is given by a commutator, and the trace of the commutator is given by this rather fascinating cubic polynomial, which I want to discuss. The Poisson structure has a very nice formula. You take the Euclidean volume form, or its dual, and you take the inner product with the differential of the boundary trace, and you get this object which represents the dual to the area form on the level sets. So we want to look at the level sets of this, and I'm now going to restrict to the real points. So K is real, and the 3 variables are. The symplectic structure on the level sets, now when the parameter is less than -2, these correspond to hyperbolic structures on the torus with one hole or a puncture. And the Weil-Petersen symplectic structure is given by this formula. The Narasimhan-Atiyah-Bott structure for SU2 arises when the parameter is between -2 and 2. And one has to look at certain components because even for those, there's going to be representations. And I should mention that the real points in the character variety correspond to representations into the 2 real forms, SU2 and SL2R of SL2C. Why should this cubic polynomial have such automorphisms? Well, it's easy to see that they're given by natural involutions as follows. This is a cubic polynomial. Its restriction to each coordinate line is quadratic. In other words, fix two of the variables, you get a quadratic polynomial. And if you know one root of a quadratic equation, then you know the other one by a simple substitution. And that corresponds to the three generating deck transformations of the coordinate projections. So this defines a free Coxeter group of three generators. And this is a very interesting example of inhomogeneous dynamics, as we'll see. I should maybe mention that these are affine cubics. This because the polynomials are not homogeneous quadratic polynomials, they don't extend to the projective space, and the automorphisms of the projective cubic will be a finite group. One particular case where you have singularities is when the level is k equals 2. These correspond to the reducible representations. And in this case, you get a rational parameterization of this cubic surface, namely corresponding to the eigenvalues of the matrix. So you can upper triangularize or diagonalize the matrix. Then the A and B parameters correspond to rational coordinates, and the traces are given by these simple rational functions. In this case, the action of the mapping class group, which is GL2Z, is going to be just acting on product of two C stars modulo the natural involution defined by inversion. And here's a picture of what this cubic surface looks like. Another case that's been studied corresponds to hyperbolic geometry. And so this case, the level is -2. The structure is going to be a hyperbolic structure on the punctured torus. So these will be finite area, complete hyperbolic structures. Notice that the origin, when x, y, and z, psi, eta, and zeta are all equal to 0, that corresponds to a point. And that corresponds to the quaternion representation by Pauli matrices in SU2. So as I mentioned, the representations, the equivalence classes, the character variety, the GIT quotient is corresponds, the real points correspond to representations in the two real forms. You have the origin, which is the SU2 representation, and then SL2R representations comprising these four components. The reason you have four components is that these are now representations into SL2 rather than PSL2, and you have four different lifts. The Markov equation, which is I wrote at the top, corresponds to hyperbolic structures on the once punctured torus that have special triple symmetry. When the parameter is greater than 2, and this is the example that I'll end with, in that case, you get an ergodic action on whenever the parameter k is less than 18. But when the parameter, the trace of the commutator, becomes 18 or gets larger, then you get wandering domains. And where does this come from? Well, the fundamental group is a two-generator free group. That's the fundamental group of a one-hole torus. And every homotopy equivalence of the one-hole torus is homotopic to a homeomorphism. That's similar to what happens for closed surfaces. But it's also the fundamental group of the three-hole sphere of a pair of pants. And a homotopy equivalence from a one-hole torus to a pair of pants defines an embedding of the Fricka space of hyperbolic structures on a three-hole sphere into this level set. And the first place this occurs will be when all three of the boundaries of the of the three-hole sphere are mapped in unipotently. And in that case, that corresponds to the finite area structure that has character 2, 2, 2. And in that case, or -2, -2, -2, and that corresponds to where the trace of the commutator, which is now a non-simple curve that intersects itself, self-intersection number is 3. That curve has its traces will be 18. So that's the breaking point, where the dynamics bifurcates. Here's a picture of the level set, which is a quite fascinating object. In that case, I drew the 24 straight lines, which can be interpreted as flow lines for some of the Hamiltonian flows. And there's certain points called Eckart points where 3 of the lines come together. And those points are exactly where that corresponds to these hyperbolic structures on the thrice punctured sphere. But now you apply elements of the mapping class group to change the marking, and you get an orbit, which is discrete, but the action is ergodic. Once the parameter becomes larger than 18, then you have hyperbolic structures on a three-hole sphere with geodesic boundary, and those will correspond to wandering domains. So it looks like a Kleinian group where you have islands of wandering domains, and then on the complement, the action is quite chaotic. So that's an example of what I think is a interesting dynamical system arising from the classification of locally homogeneous geometric structures. And I think this is a very rich and fertile area of investigation. And so I'll conclude here, and I'd like to wish Raghunathan a very happy birthday. Thank you very much.
Thank you very much, Professor Goldman, for a great talk. Thank you. Are there any questions? Hello? Hello?
Oh.
Can you hear me? Hello?
Yeah, you can hear.
Yeah, okay. So how much of this is expected to be general? I mean, this is given by one parameter that you're varying, right? I mean, so
right.
If it's a twice punctured torus, how much of this is supposed to go to? I mean, are there 2 parameters and at some?
Well, I think it's pretty closely related to a talk we heard earlier today by Books and outer space.
Yeah.
That the mapping class, that I'm just looking at the mapping class group of fairly simple surfaces, but you can't really avoid looking at out of Fn.
Wow.
Because the fundamental, in general, the wandering domains are going to be permuted by out of Fn, and there should be a correspondence with outer space, and it'll be very complicated. It looks very complicated, and the 2-hole torus looks like the first case where this should be really intriguing. Also, the five-hole sphere is another place where you'll have a rank 3 fundamental group. So it's only going to get more complicated.
Okay, thanks.
I'm finding that just looking at this level set when k equals 18 to be quite fascinating itself. And there the mapping class group is SL2Z, and that's going to be the building block. But part of the reason for looking at surfaces with boundary is that these are the building blocks for closed surfaces and more complicated ones. So this will be the start.
Thank you.
So are there any other questions?
I put some question in the chat.
Okay. Yeah. Okay, some of us will take a look at that.
Okay, I don't know what a Gelman matrix is, But the Pauli matrices were the ones that correspond to the ij and k quaternions.
And unitary bases also, Schwinger's unitary basis or unitary bases arising from Latin squares and Hadamard matrices.
Yeah,
They are
yeah,
projective representations.
maybe we can discuss it in chat. Yeah. Yeah,
Okay.
do that.
Thank you.
Yeah. Thank you so much, Bill, and we